Thank you everybody for being here again today for this seminar. Today we have a talk by Matthias Becker. He's a PhD student at Malmö University in Sweden. He's working with Thomas North, and he will be entertaining us today on the contention-free execution of automotive applications on cluster mini-core platforms. I guess we have around 30 minutes to entertain us on this subject.
Thank you for the introduction. As Patrick already said, today I'm talking about contention-free execution of automotive applications on clustered mini-core architectures. And this work was done together with Virginia Dasari, Boris Nikovic, Ben Orkison, Vincent Nellis, and my supervisor, Thomas North. So let me start quite general. What is a mini-core platform? What do I mean when I talk about mini-core platforms? And in general, we can say that on a mini-core processor, we can find several tens, but more likely hundreds or even thousands of compute cores on one single chip. Or we can also say that it's basically like a distributed system squeezed into a single chip, which fits really well. So if you take this distributed system view, we can see that we have several compute platforms. Each of those can host several processing units. Inside those, we can also find local memory, and of course we have a network interface, so they all connect via some sort of network. So now we squeeze it onto a single chip, and we add some external memory, and since it's a silicon platform, it's a bit more organized usually. So we have those orange squares, so-called tiles, and each square basically has the same as the platforms from before. We can find again processing units, local memory, and the network interface. And such so-called tile connects to a network on chip router, the brown boxes here. And all those routers connect to each other, forming a network again. So again, we have basically the same characteristics. Why are those platforms nice? So usually we get a large boost in compute power, just because we have so many different compute cores on one single platform. But we also are more power efficient compared to single or multi-core platforms with the same computational power. And that's because we can clock each CPU with low frequency, which then affects the power consumption. So it seems really nice. We have a lot of performance and we pay less energy consumption. But of course we have to keep in mind that we have timing requirements. So it's not as easy as it might look like. So basically for real-time systems, guaranteed performance is important. But unfortunately, most of the COTS platforms are designed for average performance just because it's a different market in mind. So basically, to use these many-core platforms in real-time systems, either we have to account for the worst case, or we have to somehow prevent this worst case. And that's basically what I'm going to talk about. To the outline of my talk, first I will describe how my automotive applications look like, what we can find there. We will talk a little bit about the communication model. Then I will talk about the clustered many-core platform, give more details, how this looks like. And then we reach the main part, where we talk about the execution framework. We have some rules, and then we talk about how we generate our schedules. And then lastly, we will evaluate our system, and then conclude the talk. So automotive applications, in particular here we are looking at AUTOSAR applications. AUTOSAR is de facto standard for automotive applications in the European and North American market. And basically they describe how to develop such systems. And in AUTOSAR we can find schedulable entities. Schedulable entities in AUTOSAR are runnables. And those runnables, they must communicate to fulfill the system functionality, and they do that by global variables. And in the automotive context, we're talking about labels. So global variables are called labels here. Then if you look into one of those ECUs, usually we can find a lot of those runnables. So each of those squares is a runnable, and each connection line is basically communication over a shared variable or label. So it's quite complex. Engine management system, for example, can have up to 2,000 runnables, and those 2,000 runnables, they communicate with using 50,000 shared labels. So it's a lot of stuff which is going on there. So usually runnables are not what the system engineer is working with. System engineers, they work with software components because they're reusable. And the software component then in turn is built up with several runnables to fulfill its functionality. What's interesting is that each runnable can be described with the, basically our task parameters, so we can find worst case execution time, period. We have implicit deadlines, but then also we can find a footprint, which is the size of the code in memory, but also some set of labels which are accessed during its execution. So why not just kind of merge all the runnables which are inside one software component together? So we can't do this because usually the runnables inside one software component can have different periods, so we can't just merge them. Then in AutoStar, I already mentioned that we're communicating via shared variables, but there are actually two different kinds of mechanisms defined in the standard. We have at one hand explicit access, and on the other hand implicit access. Both communication forms describe how and when runnable accesses a label during its execution. And while both are still valid, the implicit communication is most used in control applications. So in this work, we only focus on implicit communication. And what does this implicit communication look like? Basically, in this implicit communication form, we can divide the execution of one runnable in three distinct parts. We have read phase, execute phase, and write phase. During the read phase, the runnable makes local copies of all labels which are read during the execution. During the execution phase, each access to this label is access to this local copy. And then in the write phase, the runnable updates the shared labels in the shared ones. Why is this nice? Basically, for control applications, it's nice because consecutive access to the same label during execution phase always yields the same result. So even if some other runnable changes the value of the global runnable, from perspective of this job's execution, nothing changes. And apparently that's good for control applications. Now if we look into our hardware platform, our cluster many-core architecture, as I said before, we have hundreds of compute cores on one processor. And to make it more organized, in our particular case, we have clusters. Each cluster has 16 compute cores and one resource management core. The compute cores are usually intended for computation, and the resource management core is intended to organize the access to other clusters or to off-chip memory over the network on chip. So we can see that each of those blue squares is one cluster, and they're all connected via the network on chip. Now, hardware-wise, both core types are exactly the same. So it's the same core implemented for resource management and processing element. It's just this logical decision that one of them is special purpose. When we look into the cluster a bit more detailed, we can also find some shared memory. In fact, we have local memory arranged in 16 different memory banks, which basically yields one memory bank per execution core. But unfortunately, this memory is not large enough to host our automotive application. So our application is larger than this 2 megabytes, which we can find inside the cluster. So we have to use some off-chip memory, which is, of course, larger. But it's also much slower because now, when one of the cores here wants to access something out here, we have to go over the resource management core, over the network, over this I/O subsystem, which connects to the memory, and back. So it's much, much more expensive. And further in this work, we only focus on one cluster. So for now, all the other clusters are idle, which also means that there's no contention on the network on chip. Since the main focus is on the cluster, we go a bit more into detail here. As I already mentioned, we have 16 memory banks, and each memory bank can be accessed from any core. to handle this access, we have some arbitration mechanisms. In fact, we can find 4 levels of arbitration for each memory bank, and it looks exactly the same for any memory bank. And then we have the 16 processing elements which may access resource management core, receive and transmit of the NOC, but also the debug support unit which might interfere with our execution. So now the question comes, what's the worst case which can happen here? So how much interference do I get in the worst case if all the others kind of execute in the same time as I do? And it turns out, in the worst case, it takes 1,575 nanoseconds. And on the other hand, in the best case, it takes just 25 nanoseconds if no one else is executing. So it's a large difference. And yeah, it's a factor of 63 times longer in the worst case than in the in the best case. This means if we would look at it in a naive way, we could just increase all the memory access times and our execution times by a factor of 63 and we're fine. But then we would most likely lose the advantage of our platform because we just waste a lot of cycles. So we would like to somehow prevent this. And we do this by our contention-free execution framework. And our framework is built on 3 pillars. On the first one, we have the memory bank privatization, which we exploit. Then we exploit the read-execute-write semantic of AutoSum. And we organize everything using a time-triggered schedule. And now I will go more into detail, and then basically it becomes hopefully clear how all of those play together. So coming to the memory bank privatization, here we have a dummy cluster. To make it easier, we just have 8 cores and also 8 memory banks. Now I said that we have exactly the same number of memory banks than cores, which would, basically it seems we can just do this one-to-one mapping of banks to cores. But then we have to keep in mind that we have those global variables we have to assign somewhere, and those variables are potentially accessed from any core. To overcome this limitation, what we do, basically we turn off one core. So we have this additional memory bank. And this memory bank is only used to basically store all the global copies of the labels. For all the other cores, we perform a logical one-to-one mapping, and we can enforce this on the real platform using linker script, so that's no problem here. Then in this case, we have just one memory bank for all the global variables, but of course, if the size of all the global variables is larger than what we can fit here, we can just turn off one more core and we have one more laser bank. Now, once we know that we have this private memory bank, which is assigned for one runnables execution, we can tie it together with the read-execute-write semantic. So basically, what we need to do in the read part is, as I already explained, that we make those local copies. So we copy from the global memory label bank into our private label bank. But now we also need to get the codes here somehow, and the code is located off-chip at the moment. So we have to access the network on chip and load the code into our private memory bank. Now during the execution phase, we can just operate on everything which is in our private memory bank, and we don't have to access any other bank. So here there is no interference, which is nice. But then at the end, when we come to the write phase, we have to, of course, update the shared memory again. So we have to copy those. And then some of the data which is loaded from off-chip needs to be brought back as well. So not the code, but the private data of the runnable. So we have to access the network and chip as well. And here we can also see that at the end of the execution, there's basically nothing left on the private memory bank. So successive instances of my runnable can be executed on any core, so we have no runnable to core mapping. Yeah, now basically coming to the time-triggered schedule, we use a time-triggered schedule to organize our execution. As I said before, we have this resource management core, which is intended to handle network on chip access, but we can of course do anything on this core. So this core is used to organize our time-triggered schedule, and our time-triggered schedule basically organizes the access to our to the limited resources, which in this fact is the off-chip memory and the shared memory. So all this copying of labels to from the global label bank to the private bank, and to copy the code from off-chip to on-chip is organized by this resource management core. And this is basically done because the main challenge is the memory access and not the execution, since the cores are plentiful available, whereas the shared global, the memory is the shared part, basically. To do this, we defined a heuristic. We called it memory-centric heuristic, so MCH. And basically, the heuristic is defined based on schedulable entities, which are based on one instance of a job. So out of one execution of one runnable, we make one read job and one write job, and those must be scheduled on the network, on the memory. With memory, I mean any memory access. This also means that the read and the write job must be sufficiently apart. So I just need to make sure that I don't schedule both of them closer together than CI execute time units. And of course, the write job must finish before the deadline comes. Then at the beginning of the heuristic, we generate all the read jobs which must be executed during the hyper period. This we can do because we know once the runnable instance is released, the read job is released implicitly. We don't add the write jobs because we don't know when to schedule the write jobs at this point. Then when it comes to assigning jobs to the memory, we initialize some local time for our algorithm to 0, and then basically at each time when we want to add something to the schedule, we have to consult some rules. And out of all released jobs, we get the write job with the earliest deadline and the read job with the earliest deadline. And then we compare. If all cores are busy, we always schedule the write job. If there is a core, but read and write job have the same deadline, we prioritize the write job. And otherwise, if there is a core available, we select the job with the earliest deadline. We prioritize the write job because scheduling a write job frees up a core, whereas scheduling a read job allocates more resources. So, for example, in this case, if all cores are busy, I can't schedule a read job because each read job needs a core. But scheduling a write job, on the other hand, frees up a core, so I would like to get more resources. Yes, and then once I selected one job, I assign it to the memory schedule, and I increment my logical time by the respective execution time of this memory job. Then, on the other hand, once a job on the memory completes, basically we have two cases. A read job can complete and a write job can complete. Once a read job completes, the corresponding write job is generated, but not released yet. And basically this write job is generated to be released via execute time units after the point after the current algorithm time, just to make sure that there's enough time for execution of the runnable. On the other hand, if a write job finishes, basically what we have to do is we have to free the core again, and we need to check if the deadline is met of the runnable. If not, we can stop at this point because it's unschedulable. Yeah, and to make it a bit more understandable, I have an example. Basically, we just have a really small task set, 3 runnables. All memory access phases are 1 time unit, and we only consider a platform with 2 cores. This also means we have the memory, so actually we have 3 things in our time access, so we have to schedule the memory, core 1 and core 2. At the beginning, of course, the release jobs are empty, because there was no actual execution yet. So we start initializing our algorithm time by 0, and now we can see that all those jobs are the same time as our algorithm time, so we can add them to the release jobs queue. And of course, since both cores are empty and the memory is empty, we can actually select a job out of the release jobs queue for execution. And in this term, the blue job has the earliest deadline because the next instance is released at time instance 6 again. So we add it to the memory. We also add it to the, basically we mount it at the core, but there is actually no execution on this core happening because yeah, it's just that we are not allowed to use this core at this time because someone else is accessing our memory bank. And to be contention-free, there is no two executions to be allowed at the same time. Once we did this, we just increase our logical time. Now we reach this point that our read job finished. As I said, once the read job finished, we have to generate our write job. And the write job basically is set to be released CI execute time units after the current time, just to make sure for the execution on core 1. Additionally, we have one empty core and the memory is empty, so we can select another job out of the list. And this time it's the green job. So we add it to the schedule and mark it on the core and increase the time again. Now, yeah, basically the execution of the read job finished, so we add the write job here. We account for the execution time, but we can't assign any new job to the system, even though the memory schedule would be empty, but we don't have any core to assign it to. So we increase the time. Now we have the problem that, again, the core is not empty, whereas the memory is empty, and this write job respective to our current algorithm time is released, so we have to add it up there. So we just schedule the write job, increase the time, and now finally we can schedule this yellow job, and so on. So I skip the rest because it takes really long. And yeah, we can see once we reach the hyper period, which is 24, there is no job up here. All the jobs are finished. So basically we can return success because we found a valid schedule. What may be interesting is that we have this kind of hole here in the last execution of the blue job. And while this is valid, because the deadline of this job is 24, so basically it means that the white job does not need to be as close to the execution phase as possible. It's just that we basically lock the core down for longer than we would have needed necessarily. Since this was just a heuristic, we also formulated the same problem as ILP. Basically the problem which needs to be solved is that we need to find the mapping of jobs to cores. We have to assign the memory access spaces, and basically memory access spaces are not allowed to overlap. Read and write phase of the same instance must be sufficiently apart, and of course we must meet all the deadlines. Since we only want to find the schedule, we don't need to care about any optimization, so we can just put maximize 1 as optimization function. And the nice part here is that if a solution exists, we will find it, so we are optimal. But on the other hand, we have the well-known scalability problem. So once the number of my runnables increases, the execution time or the solving time of the ILP increases a lot. So coming to the evaluation, we have a set of experiments. First, I will talk about synthetic experiments. Here we generated random runnables. The period of those runnables were chosen based on distributions commonly found in automotive applications, and the utilizations were generated by Unifast. In each runnable set, we have 100 different runnables, and for each data point, we generated 500 different sets. To compare our heuristic against some other heuristic, basically we also described baseline heuristic, which is core-centric heuristic. And this core-centric heuristic treats the cores as basically level 1 citizens, whereas our heuristic treats the memory as level 1 citizens and the core schedule falls out. And we will see how they compare against each other. So in the first experiment, we look at different numbers of cores in one cluster. So on the x-axis, we vary the cluster size. Then we assign runnables to the system. So basically each runnable, since we generate the complete execution time by Unifast, by the system generation, we have to come up with the size of read and write phase. And in this case, we selected the read phase and the write phase to be 5% of the complete execution time. And the execute phase is basically 90%. Then we try to schedule those systems. And as you can see on the y-axis, we have average last schedulable utilization. And what we mean here is that once our system is schedulable, we inflate the execution times of all runnables until we find this last schedulable utilization. And then here we show the average out of all those values. We can see that the core-centric heuristic, or comparison, is the red line, and it does not perform so well. So we see even if we add 14 cores to the system, the utilization is not even larger than 1. So we underutilize the system a lot. On the other hand, we can see that our memory-centric heuristic performs really good at the beginning, but then at some point we reach saturation. So we have this a point where adding more cores to the system is not increasing the performance. And that's the case because the memory schedule is utilized so much that there is no space to add any new read or write phase. So we can't add anything here. Then in our second experiment, we kept the execution, the number of cores constant, but we varied the memory exit percentage. So before I was saying that I had 595% exit distribution, and here basically that constitutes to this 0.5 here, whereas yeah, we also looked at 10, 15, 20, and 25%, whereas 25% means that I have only 50% of execution, so the memory access is quite a lot. And we can see that yeah, as expected, if I increase those phases, the schedulability drops, or the last schedulable utilization drops a lot for both heuristics. But on the other hand, if yeah, we have a smaller memory access percentage than what we had before, we can see that the core-centric heuristic still does not manage to exploit this, whereas our heuristic yeah, can exploit more and more the basically potential of the platform. This is just because for the core-centric heuristic, the cores are scheduled and then the memory schedule falls out. So I have a lot of fragmentation on the memory schedule, and I get this, yeah, all those gaps which are not large enough to put additional memory access, but are just wasting utilization. On the other hand, when we have our heuristic, where we basically build this memory schedule and the core schedule falls out, we can yeah, use the potential of the system much more. Yes, so basically less memory traffic equals higher schedulability. Then, since until now we just compared the two heuristics, we were looking at the solution quality. To do this, we compare against the ILP. And since the ILP is involved, we have this issue of scalability. So here we just look at runnable sets which include 100 jobs in total. We have also 15 shared labels in the sets, and we generate 100 random sets based on these parameters. Then what we can see is basically we noted the average solving time, last schedulable utilization as before. And then in the last column we have the basically improvement of hours against the others. We can see that while we clearly outperform the core-centric heuristic, we perform a little bit worse than the ILP. But on the other hand, we can also see that we are much, much faster than the ILP. So basically, taking this industrial applications, we might be able to deal with this worse performance because we gain a lot in the computation time. And that's basically, basically the memory-centric heuristic scales up to industrial-sized applications, hopefully. So that's what we look into now. So we also perform the case study. As hardware platform, we choose the Carrier MPP8 256. So all parameters we choose in the case study are based on this in this processor. Each memory bank here has 128 kilobytes of space. We allocated 2 banks as label banks, which left us 14 cores for execution. And everything is clocked with a CPU frequency of 400 megahertz. Our application was an engine management system, because engine management systems count to the most complex applications in the automotive domain. In our system, we can find 2,000 runnables, which led to 171,631 jobs, which we need to schedule in one hyperperiod. And if you remember, we have to schedule basically 2 units per job, so actually we have almost 300,000 things to schedule. All those runnables communicate using 50,000 shared labels. And out of those 50,000 shared labels, we have 40% which are only accessed by reading, 10% which are only accessed by writing, and 50% which are accessed by reading and writing. So why is this important? Basically, if I have runnable access for reading and writing, the two copies are made, one which are for reading and one which is intended for writing, because the reading always needs to yield the same result. So if we try to schedule this now with our memory-centric heuristic, we found that we can find a schedule after 52 minutes on my computer. And we utilize basically all the 14 cores, and the utilization of the different cores is between 23.3 and 26.1%. And the memory schedule, basically the memory access, is utilized by 26.4%. On the other hand, if we try to schedule with the core-centric heuristic, we can't find a schedule. So we try to kind of adjust the hardware parameters to see at which point do we actually make it schedulable. And it turns out we have to either increase the core count of the cluster to 96, which is increased by a factor of 6.64, or we have to increase the frequency by a factor of 8. So both of them don't seem doable, because it would underutilize the system even more. On the other hand, we also tried to use the ILP, but unfortunately even the first 1,000 jobs within the schedule are not doable in the first 64 hours, so then we stopped the experiment. Yeah, this leads to the conclusion. So basically, we can see that many cores provide a lot of potential for embedded and real-time applications. We have a large number of possible interference. So either we have to heavily inflate our worst-case execution times, or we have to find execution paradigms which kind of circumvent those issues. So we need to be contention aware. This led us to our contention-free execution framework, which is built on the 3 key points that we have: privatization of local memory banks, we have the read, execute, write semantic, and then we orchestrate the whole memory access using our time-triggered schedule. For future work, of course, for now we just utilize one cluster. So in the future, we would like to use the whole potential of the platform. So we would like to add one application per cluster that I can actually utilize the whole system. But then we will also need to take more details of these automotive applications into account. So for now, we just have the deadline of each runnable. But actually in automotive systems, often you also have timing constraints on a chain of runnables. So basically the data propagation through a chain of independently triggered runnables needs to be taken into account as well, which needs to be taken into account for our heuristic basically. And that leads to the end of my talk. Thank you very much.
We have time for a couple of questions.
Very good talk, very good work, thank you. I have a basic question. We have read phase, execution time, and then write phase. And if I understood correctly, in read phase, we take a copy of shared labels which are somehow in a global place. So what if 2 tasks at the same time want to access one shared label? So actually the main question is how the concurrency mechanism is like guaranteeing mutual exclusion on the shared variables.
That's basically because the heuristic makes sure, or how we build the time-triggered schedule makes sure that this read and write phases never overlap. So even the read and write phase from different cores, they are never allocated to the memory access.
Even in your example, I could see, for example, the first task starts to read. Just imagine you go for reading variable A. Then the second task read here down the blue part and the green part.
Yes.
So imagine there's a shared variable A read by the first task. Also, this variable is also read by the second task.
Yes. Basically, we had this in before, but then we returned to the standard, and in the standard, basically, they define that you always read the actual variable. So even if someone has a local copy, you don't really care about that, and that's defined by the standard.
So what if I change it, like the first task change A to 10, then the second task change A to 20, and then they both want to write. A comes, like first task it's...
Basically last is best in this case.
Oh.
But that's how they define it. So we were also quite surprised. Because we had to change.
Is it really working?
Apparently. Because usually the execution times of those runnables are really, really, like in microsecond range. They're really, really, really tiny.
I had the impression that in AutoSAR they also define the fact that you need to ensure mutual exclusion. So
yes, but then you need to define this on the runnables and on the labels.
Exactly. So, but could you extend your heuristic to consider that?
Yes, actually we had in the first version we considered it, and then we got feedback that you don't really need to consider that. Because it's not in the standard, so we removed it again.
AutoSAR allows race conditions?
Yeah, in this case, basically, if you access this values, it's always last is best. So that's how they define it.
Who was the feedback?
We don't know. Reviewer.
Really?
It's a different perception, like you don't have an explicit precedence constraints dependencies, it's just you can have less and more fresh information.
No, but I had the impression that AutoSAR specifically says that mutual exclusion must be ensured. So you must have a mechanism for mutual exclusion, like a locking protocol. So I have the impression that AutoSAR writes it explicitly in the standard.
Yeah, you have this locking protocols, but then in your application you have to do this additionally. The communication forms, they don't really care about this.
That means that you have to consider that when you build your schedule for the read and write phase 2.
Yes.
Because
if the application
it's not
defines it.
sufficient to just have an exclusion protocol at the execution phase. You have to ensure the consistency of the data at the end also.
Yeah, basically it would be kind of a second level. So for now we just look at access, but in the application someone would need to actually basically set up the lock and then access it. And this is what we're not taking into account at the moment.
So that comes back to say that instead of having a lock which is put during the execution phase, the lock must be put directly from the reading phase.
Yes.
So before the reading phase.
Yeah, okay. I have a question. Why do we not? So one thing that you have shown in your simulation. So we use 15 cores to run, or 14 cores to run the runables, and then we disable 1 or 2 cores because we want to take their bank to make a shared bank, like the bank which will contain all the shared labels. And one thing that you show in your experiments is that these 2 banks are really the bottlenecks. Okay, so. And when you use more than 8 cores to run the runables, basically you don't improve the performance.
Yes.
Okay, so why not, instead of taking 14 cores to run the runables and 2 cores that you disable to take 2 label banks, why not using 8 label banks and 8 cores to run the runables, and then try to distribute the interference, so map the label differently across these 8 label banks so that you will reduce the interference.
Yes, that one would be a nice approach, but you could also just go and kind of group runables together and then form these groups of execution. Because usually the footprint of the runnable and the labels is quite much smaller than what we can fit into one bank. So we could just put them together, form this kind of bigger entities, and then fill up the banks completely, so we don't pay this much for accessing the off-chip memory as well. And then you would circumvent this. What I showed in the experiments, this 5% is also quite a lot. So usually we are more on the smaller side.
Just an observation. Actually, I fully agree with what Vincent said, because you can go one step further and analyze the the workload that you have, whether it is execution-centric and memory-centric, and based on that derive the best ratio of your cores, which one of those are dedicated to execution and which for storing labels to achieve the best results. And that could be something to...
Maybe what we could do, okay, apparently if you use more than 8 cores, it's not very useful. You don't gain anything in terms of performance for this specific use case. So maybe we can just disable 8 cores, and with these 8 banks, we can use 1 for the labels, or 2 or 3 or 4, and then we could also use 1, 2, 3, 4 to already preload the code of the renewals which are about to be executed. So we have kind of a prefetch mechanism installed just on 4 banks. So then the renewals before running, they will take the shared label in the shared bank, and we make sure that their code is already ready in some other bank, so that they don't communicate with the off-chip memory.
Yes. Yeah, basically what you also could do is just keep the code in local memory. Because we have kind of distribution of periods from 1 millisecond is the smallest usually in automotive, and 1000 millisecond is the largest. So then in my happy period of 1 second, I would fetch this code for the 1 millisecond runnable 1000 times from off-chip. So if I keep it on my local memory, then I get a lot of performance just because I shrink this memory access times a lot.
And what is the footprint again of all the renewals together? The instruction for the code?
The code itself is like 4 point something megabytes.
So we cannot even keep it in the shared 2 megabytes of the next cluster, for example?
No, you would need to.
Okay. And just the last thing, these numbers about the best case latency and worst case latency for memory access, is it the numbers that...
That's theoretical numbers, not measurements.
Because we came up with some numbers like this at some point, you know?
Something like that.
And we have numbers... Because
I think those are the numbers. I think those are the numbers in the ratio of 63 or something.
Yeah,
Yes.
The numbers are basically what Benny computed.
They are?
What Benny did.
Yeah. Like this is more justification. Okay. Because 1 year ago we ran experiments to try to get those numbers, and we got some, but I don't remember the numbers we got.
It was similar.
It was like something.
Yeah.
Okay.
Okay, thank you.